Galt from Math Department here, telling us about dimensional reductions and adiabatic limits of generalized ASD connections. Thank you, Jill.
All right, well, thank you for the invitation. It's very nice to talk at CMSA here. So everything I'm going to talk about today is joint work with my collaborator, Langte Ma. This is part of a sort of long-term project that we've been working on together. And a point I want to emphasize, which I'll come back to later, is that essentially the problem I'll describe today is sort of a local version, sort of a global version of a local problem, which is itself a local version of a global problem. So that sort of, I'll try to explain what I mean by that. So first, let me give you the setup. And then, so to explain what I mean by dimension reduction. Then I'll give the examples that we're most interested in and kind of talk about how this fits into sort of more broadly what people care about. Then I'll talk about our results, and then in the end I'll talk a little bit about some work in progress, trying to sort of extend what we've done. Okay, so I'll start quite generally. So I'm going to suppose that I have a principal SUR bundle over a closed Riemannian manifold, so compact without boundary. And then I have the space of connections. Okay, so this is the affine space of connections on P, and I have the gauge group. So this is the group of automorphisms. And with this data, I have this so-called Yang-Mills functional. So let me fix the connection that I'm working with an SUR bundle. So let me fix the convention that if I have two Lie algebra elements, I want to fix the norm in this way. So this is sort of just because I'll write some formulas later.
You didn't take the trivial bundle, right? But since later you assumed it's trivial bundle.
No, not necessarily, yeah.
Okay.
This is just an arbitrary, right now just arbitrary bundle. Okay. So what is this Yang-Mills functional? So this is a map. This is a functional on this space of connections modulo gauge. Okay, and it's given by taking the L2 norm of the curvature. Okay, where this L2 norm is defined using this Riemannian metric and this metric on the Lie algebra I've just specified. Okay, so we're interested in absolute minimizers of this functional. So I'm going to describe a kind of general, these so-called generalized ASD connections are examples of absolute minimizers. And these have been studied for quite a while, but the picture that I'll sketch is sort of essentially following Tian's original paper in 2000, the definition I'll give. Okay, so what are these so-called generalized ASD connections? Okay, so I want to take an n-4 form on M. So now n is at least 4. And I'm going to consider the corresponding endomorphism of the two forms, which is given by taking a two form, wedging with this theta, and then taking the Hodge star on M. Okay. So definition, a connection is theta anti-self-dual if it solves the following equation. Okay, where this lambda theta is the minimum of the spectrum of this operator. Okay. So one can make this definition in general. Okay, but in order to arrange that these solutions actually minimize the Yang-Mills functional, one needs to make some assumption in particular, so that you want this lambda theta to be an eigenvalue. So what we'll restrict ourselves to, one can work sort of slightly more generally for this, but this will include all the examples that we care about. So what we'll restrict ourselves to today is...
Is it related to theta being closed?
It is, right, yeah, right, exactly, right. So I'll call theta admissible for our purposes if it's parallel, and then up to scaling, I just want to normalize this eigenvalue to be -1, the minimal eigenvalue. Okay, and then what you can show in this case is you can essentially just redo the classical argument for anti-self dual connections on a 4 manifold. The parallel condition tells you you have a decomposition of the bundle of 2 forms into eigen subbundles. Okay.
Parallel sounds very strong. Like
it's very restrictive, right? So there are, I mean, for special theta, you can prove they're minimizers without this assumption.
You didn't even introduce the metric. You just introduced the H star.
Well, I mean, in higher dimensions, it's not necessarily conformal. I need a metric.
Yeah. But I mean, I could change the metric.
You could change the metric, yeah, you could. I mean, for instance, you might be concerned that sort of I scale theta to arrange this, but the metric might have a different sort of scaling power. Okay, so, but for the examples we'll care about, it turns out this is actually always true. Yeah. So I'm not sort of trying to pursue the most generality at this point, but so this restriction will make things convenient, and it will suffice for what I'm going to describe.
Do you know any example of generalized anti-self-dual instanton, which is not just one of the more well-known examples that appear in, like Kähler or holonomy?
No, I don't. Yeah. I think we thought a little bit about whether you can come up with more. So the point is that somehow, if you work with this parallel condition,
probably it just
then
implies there is a reduction.
Yeah, right. Then you have
structure.
Yeah, so if if you work with this parallel condition and this form has some stabilizer, then you get a reduction of the structure group. Yeah. So you're working with special holonomy. So answering that question requires you to specify a form which is not parallel, but for which you still have a reduction here. I think there are some. Yeah, I don't really know any examples of that.
Yeah, it might be that there wouldn't be any motivation.
Yeah. Okay. So, yeah, right. So as you're saying, the motivation for us is really special holonomy. Okay. So let me say. So in this case, which is to say, in this admissible case, we will say A is a theta instanton. And in fact, you can see that the Yang-Mills functional is bounded below by this topological quantity where I cup the second Chern class with theta and I pair with M with equality if and only if A is a theta instanton. Okay. So they indeed absolutely minimize. Okay, so let me try to describe the dimension reduction setup here. Okay, so what do we mean by dimension reduction? So for our purposes, dimension reduction will mean the following thing. So I'm going to suppose that M is a product now of 2 closed manifolds with the product metric, where Q is at least 4-dimensional. Okay. And now Y and X are closed Riemannian manifolds. Okay. And then I'm going to suppose I have an admissible form theta, which I'm moreover going to suppose is in the following form. Okay, so now notice you can always write theta in this form. I'm just writing out, I'm just looking at the type decomposition of theta using the type decomposition of forms induced by this product structure. But what I want to assume is that I have theta written in this way. So right now I'm not assuming anything, I'm just writing theta in this way, where this alpha has no p q minus 4 part. Okay? And then what I'm going to, so definition, I'm going to say such a theta is compatible, so it's compatible with this product structure if lambda beta is equal to lambda theta. So this beta is a q minus 4 form on X. So I can look at the associated notion of a beta anti-self-dual connection. Okay? And this compatibility assumption is that the eigenvalues are both the same. So in particular, they're both equal to -1. Okay. Now it'll turn out that actually it's only interesting if you assume this. So I'll explain that in a second. So this might seem a little bit ad hoc, but it's actually not. It's actually not. Okay. All right. Okay, and what is the goal? So I want to look at this moduli space. So I'm looking at connections on P, which solve this theta instanton equation. Modulo gauge equivalence. And then correspondingly, I can look at connections on X, which solve the corresponding equation. But now they are with respect to this form beta. Okay, so where this Px is some reference bundle over X, and it satisfies the so I pick this bundle to have the property that it's isomorphic to the restriction of P to any slice. Okay, so all these bundles are isomorphic. I just pick some reference bundle, and this is the moduli space I define. Okay, I actually want to restrict myself. So we have a statement for reducibles, but I want to restrict myself to these irreducible loci here. Okay. All right, so this is a SUR bundle. This is a SUR bundle. I'm looking at these irreducible connections. And these are, so these spaces might not be smooth, but they're finite dimensional. And so they're essentially, so they're finite dimensional, sort of real analytic varieties. So it makes sense to ask, sort of, are they homeomorphic? Can their Zariski tangent spaces be compared? This is the level at which we'll consider things. Okay. Any questions? Okay, so I'll state the result in a second, but let me give some examples. One could kind of spend a long time giving these examples in detail, but I don't have infinite time. So let me. So as we were saying earlier, the way that I've set things up suggests that the interesting examples should come from manifolds with reduced holonomy. And indeed, the reason we were initially considering this is because we're interested in studying these generalized anti-self-dual connections over special holonomy manifolds. Okay, so why are we interested in these product examples? Well, one way that these compact manifolds with special holonomy are constructed is by taking something which is singular and resolving the singularities. And when you resolve the singularities, you usually glue in something which is like a compact Y cross some non-compact X. Okay, so you can sort of try to produce instantons on such a space by sort of gluing in instantons on the models. There are results of this form, for instance, by Thomas Walpusky. So the reason I say this is sort of a global version of a local problem, which is a local version of a global problem, is that here we take X to be compact. Okay, but what you'll see is, well, the proof that we have for our main results is rather geometric, so it's easy to imagine a certain form will hold for non-compact X, and then that this might be useful for gluing problems. Okay.
X would be the normal bundle in the global.
Yeah, X would be like an ALE space or something like this, yeah.
Or one might say this is just an example where the analysis works.
Yeah, right, so you could think, why not at least do it in this example where everything is a little bit simpler. Okay. So, so what are the special holonomy spaces we're interested in? So let me give examples here. Okay. So let's consider the case of dimension 7. So in dimension 7, I want to think of the linear model. I want to think of R7 as the imaginary octonions. And this has a cross product, which is given by induced from octonionic multiplication. And so I can define a special 3 form by the cross product and then the Euclidean inner product. So definition, so a 3 form on now on an arbitrary sort of smooth 7 manifold is a G2 structure if phi is pointwise equivalent to this phi naught. Okay, and why is it a G2 structure? Well, the stabilizer of this phi naught is isomorphic to this Lie group G2. Okay. So this is the same thing as saying that I have a reduction of the structure group of my frame bundle to G2. Okay. Now, this phi will determine a Riemannian metric, and if it's parallel with respect to the Levi-Civita connection for this Riemannian metric it induces, then the holonomy of that metric reduces to a subgroup of G2. Okay, so one is interested in, for instance, in these to come up with examples of with holonomy, one of the exceptional groups in Berger's list, this Lie group G2. Okay, now in this case, what is the corresponding notion of theta instanton? So a connection A on this bundle P over M7 is a G2 instanton if it solves this equation where the theta I take is this, is this form phi.
Is it for every theta? Is it always equivalent to wedge with H star?
Yeah, it is. Yeah. Oh no, not for every theta. No. That's a crucial problem. Yeah, that turns out to be a crucial problem. I'll come back to later. Yeah. So there's another way to formulate this equation, which maybe I will not mention. But in this case, notice I have not assumed that phi is parallel or anything. I just have a topological G2 structure. And I still get eigenvalue -1. Okay, so.
But in parallel case, that is correct?
No, it's not correct. Yeah, there's no corresponding notion. Yeah, for this theta instantons. Okay, so so these G2 instantons have been widely studied.
Okay, so that's really because 7 is equal to 3 plus 4.
Well, that kind of has more to do. Okay, that's one. Or you can say that in this case, the form theta determines a metric, but in general, it does not. Yeah.
That is true.
Right. So actually, something to mention here, which is non-trivial, is so this form phi determines a metric, and this is the Hodge star for that metric. But the determination is not, the scaling factor is not the same. So you'd kind of be in bad trouble if this were not -1, because you couldn't really arrange it by scaling, but it turns out to be. Okay, so what are the product examples? So one is I could take my M to be S1 cross a Calabi-Yau threefold, okay, where this now has a Kähler form and a holomorphic volume form, and I can write the G2 structure using these I can take this so-called product G2 structure like this, okay? And then in this case, I had these two moduli spaces, so the moduli spaces would be comparing G2 instantons on M to Hermitian-Yang-Mills connections on X, okay, of degree 0, because I'm taking an SUR bundle here. Okay, so this is one example of a product G2 manifold. By which I just mean I just mean that the first term class is 0 here. Yeah, that's
so you assumed X is compact.
For what I want to do, I'm assuming X is compact. Yeah.
No, I mean because the dimensional reduction wouldn't be Hermitian-Yang-Mills, no?
Well,
there would be an extra section which can be non-zero. It's okay.
I don't think so. Yeah, I don't think so.
I mean, the dimensional reduction of G2 instantons in dimension 3 is Hermitian-Yang-Mills connection?
Yeah.
Is the okay.
I mean, what I'm saying is that if I pull back a Hermitian-Yang-Mills connection, I get a G2 instanton. That's what I'm saying.
But it's two-sided arrow.
Well, okay, it's a squiggly arrow. Yeah. You missed the subtlety, the squiggly arrow. Yeah. Okay. So I haven't told you what the theorem is yet. So, okay. So secondly, all right, another product case I could take is the following. I could take a 3 torus cross a hyperkähler 4 manifold, okay, and I have this, so I have this triple of Kähler forms, and then I can write a product G2 structure in this way. Okay, so there is such a thing, and then the picture would be comparing G2 instantons on M. One would like to compare these to anti-self-dual connections on X. Okay. Okay, so these are some examples. Let me just make a quick remark about other examples. So there's an analogous story in dimension 8 where you look at so-called spin 7 instantons. And then the corresponding product models would give, you could look at 8 manifold, which is a product of S1 with a G2 manifold, and compare to G2 instantons, or the product of two Kähler 4 manifolds. Okay. And then again, you'd be comparing to anti-self-dual connections. And then there's another example, which is arbitrary codimension, which is you could look at Hermitian-Yang-Mills connections on a product of two Kähler manifolds, where this is M1 and M2 is the complex dimension. And then if I take M to be M1 plus M2, in this case, the corresponding form theta that you would look at is 1 over M minus 2 factorial omega to the M minus 2. Where this omega, I pull back the Kähler form here and add it to the pullback of the Kähler form here. Okay.
Is it the same as Hermitian-Yang-Mills and Calabi-Yau manifolds, or it's slightly different? Just the definition?
No, it's the same, yeah. So in this case, if you look at the SUR bundle, then being Hermitian-Yang-Mills is the same thing as being theta instanton for this theta, yeah. I think maybe that was related to what you're asking.
You have a squiggly arrow for T2, so you went from S1 to T3?
For T2, I don't know what 5 manifold to put here to write down a G2 structure. Yeah. This you can think so. This comes from the fact that SU3 is a subgroup of G2, and this comes from the fact that SU2 is a subgroup of G2.
Yeah, the subgroups of SO5 are not as written, right?
Yeah, I mean, I think there are.
Is there
Yeah, I
anything
don't know
in the,
how to do.
in the other holonomial list, the one due to Cartan, which they're not, they might be like symmetric space, homogeneous space.
For home, I don't know. Yeah, I mean, for which these examples hold. Yeah, you're right. I don't know how generally this.
Because I know people like there are spin 9 manifolds, which like falsely they were at Berger list 2.
Right.
But I know
right.
it still makes sense to study spin 9 instantons, and people do that.
Yeah, I mean, so there, for instance, I think there are these like. There are also examples in like the quaternion-Kähler case where people have looked at instantons. Yeah.
Because I mean, whenever the structure group is smaller, you can use that to decompose differential forms.
Right.
You just say it like the curvature falls inside that.
Right. Yeah. So I mean, really, what I'm using is some kind of decomposition of the forms. Yeah. But it's not. I'm not sure how. I'm not sure how useful it is to try to pursue that in full generality. Okay. So, so here's the theorem. With myself and Langte. So the theorem is, okay, so let P be a principal be an alpha null. So I'll explain what that is. This is the key condition, which I'll explain in a second. Principal SUR bundle. And let theta, which I remind you is written in this way, be admissible and compatible in the sense that we discussed before. Okay. All right. So, moreover, suppose that this. So we're looking at this moduli space of irreducible theta instantons on P, and I want to suppose it's non-empty, which is fine because otherwise there's nothing for us to study. So then there exists, so a more or less canonical isomorphism pi from, so I take the moduli space of irreducible beta instantons on this reference bundle over X, and I correct by this discrete factor, and then I map to the moduli space of theta instantons on P. So by isomorphism, I mean it's a homeomorphism, and it identifies it's an isomorphism between the Zariski tangent spaces. Okay, so these are, you can think, these are the same up to this finite sort of discrete correction. Okay, so in this example I've left up here, these are G2 instantons over this 3 torus cross some hyperkähler 4 manifold, and these are anti-self dual connections on this X. Okay. So what I want to try to do is explain to you sort of what the proof is, generally speaking, and then explain what is left to do in this case. So what is not covered by the assumptions of the theorem? Okay, so first of all, I need to tell you what this alpha null condition is. This is the case. So definition, so the alpha charge of P is this quantity here. So I take the second Chern class of P and I cup with this form alpha. Okay, so alpha null, this is the condition that this alpha charge is 0. Okay, so immediately I have some comments to make. The first comment is that if if this alpha charge is negative, or if it's 0, but theta is not compatible. So, i.e., this lambda beta is strictly greater than this lambda theta, then this moduli space is actually empty. And so there's nothing to do. So this theorem is treating sort of the first non-trivial case from the perspective of this alpha charge. The second comment is that if I take P to be the pullback of this reference bundle on X, then it's automatically alpha null. Okay. And this is just because in this case, you see this form will have type 0, 4. But just by the way I've written the theta, this doesn't have any things of type P minus 4 Q. Okay, so just for type reasons, this is 0. So somehow this is probably the case people are most interested in.
That is a reason to define compatibility.
This is a reason, yeah. Is that if you don't have this, then there are no instantons. Yeah. Okay, and then okay, I want to leave this theorem up, but maybe I'll write here if there's space. So the third thing is that when y is one-dimensional and theta, okay, so let's say results of this form were obtained by Yuanqi Wang in the case when you have a pullback bundle and for the G2 and spin 7 examples. Okay, so when I say results of this form so there are a few essential differences between our approach and Yuanqi's approach. One essential difference is that when you're looking at codimension-one reduction, the way this was sort of typically done is by exploiting some kind of functional point of view where you look at your equation and you sort of look at gradient flow of some functional and you sort of dimension reduce in this way. So this is kind of here we're working in potentially arbitrary codimension, so we don't have that perspective to exploit. So the proof is extremely different. The second thing is that sort of in the one-dimensional case, what he proves is that the G2 instanton will be the pullback of some Hermitian-Yang-Mills connection up to a gauge transformation which might not be smooth all the way around the circle. You might have some monodromy. Okay, so this factor can be thought of as recording the monodromy of sort of correcting for the monodromy of that gauge by twisting by some flat line bundle, so twisting by some flat connection with holonomy this Z mod R. Okay, so this is sort of, for people familiar with Yuanqi's results, this is how to understand what we're doing in that context, and we're inspired by his paper to consider this case. Okay, so right, okay. So maybe I'll erase this and try to say something now about the proof. Okay.
I think you can finish the talk anytime you want, whenever you think.
Okay. Well, I want to talk, yeah, okay, so we'll see how I'm doing on time. The last part is maybe interesting to people, so let me say something about the proof. I think the proof is quite nice. So, okay, so sketch of the proof.
Just a question. So when y is one-dimensional, that's how you see it. But in higher dimensional y, do you still think about H1 y as a monodromy thing? It doesn't.
Yeah, it is. It is, yeah, but it's right. You're right to think y. Okay, it'll be very clear from the proof. Yeah. I think it's. Yeah, that is something that you see. I think for a long time we were not sure how to capture that. Yeah, but it'll become clear. Okay, good. So the first thing is to have an energy lemma. So the energy lemma is this. So theta, again, is compatible, okay, and P is alpha null. Okay. So then if A is a theta instanton on P, so if A is a theta instanton on such a P, then the 2, 0 part of the curvature is 0, and the 1, 1 part of the curvature is 0. Okay, and if I restrict, so if I denote by by the restriction of A to any slice, this is a beta instanton. Okay, so this energy lemma tells you that studying these theta instantons sort of reduces to studying connections with this curvature vanishing conditions. Okay, this is the type decomposition of forms on the product again. Okay, so how is this? So I'm not gonna. I mean, it's just a short calculation, but let me just explain the intuition here. So the Yang-Mills functional, I can write it now as the sum of the L2 norms of each of these components, because this. I'm taking the product metric, this decomposition is orthogonal. Okay. Now, this alpha null condition tells me that if I minimizing the Yang-Mills functional on P is the same thing as just fiber-wise minimizing the Yang-Mills functional on X. So then all of the energy gets taken up by this component, which fiber-wise is just the restriction, is just the curvature of this restriction. Okay, so all the energy gets taken up by this, so these two components are 0. Okay. Okay, so, good. Okay, so we've converted our hypothesis to some condition on the connection.
So this is similar to the functional argument you said is in the codimension-one paper. Is it what playing the role of that?
So. Yeah, so in the codimension-one paper, something very unfortunate happens, which is that there's no 2, 0 part of the curvature for type reasons. So because you never see the 2, 0 part of the curvature, you'll never ask yourself, what does this vanishing mean? So I'll now explain what it means, and then it will be clear why this sort of monodromy condition comes up. Right, so what you need is you need an integrability theorem.
You mean F20 on G2 manifold, you never see that, right?
No, I mean that if you have S1 cross some manifold, yeah, then you just don't see this part because this is on the S1 factor. Yeah. So okay, so the way to set things up is to think of this manifold as a trivial fiber bundle over Y, and to push everything down to Y, and then to reinterpret these conditions. So what I mean is the following. So I have this bundle over Y cross X. Okay. On the other hand, I can project onto the Y factor, and I can think of this as a family of bundles over Y. So I'll refer to this as the family bundle. So I'll call this P underline. So this is a family of these px bundles over Y. Okay. Now let's suppose that my A is a theta instanton on P. Okay. So then, by this energy argument, the 2, 0 part of the curvature is 0. So what this means is that I look at the Ehresmann connection that this A induces on this bundle. Okay, so this connection induces. Maybe I should write it here. So A induces an Ehresmann connection on this family bundle. And then this vanishing of the 2, 0 part of the curvature tells me that this induced connection is flat. And so in particular, I can look at the holonomy of this connection, which is a map. So let me just fix a base point, which is a map to this gauge group of the reference bundle. Okay. So this is a sort of horizontal holonomy of the connection A. So this is the way to include sort of monodromy around Y. All right. Now, what is the FA11 condition? Well, this is quite fascinating. Oh, this is equals 0. Okay. Well, this goes over to the condition that the image of this horizontal holonomy representation lies in the stabilizer of the connection restricted to this fiber over the base point. So a priori, the holonomy just maps into this infinite dimensional Lie group, but the 1-1 component vanishing tells you that the holonomy actually stabilizes this restricted connection. So in particular, if I restrict the connection here, I can parallel transport it around Y using this Ehresmann connection. Okay? And this stabilizing condition tells me that that's well defined. Okay. So this map pi is constructed by parallel transport. So I fix some reference theta instanton using the fact that I've assumed the moduli space is non-empty. And then I parallel transport a beta instanton around Y after potentially twisting, and then I twist it by some flat connection that I pull back from Y. Okay, and the claim is that this is an isomorphism. So
the choice of this reference connection matters in the definition of isomorphism? That's the only thing, right?
Yeah, right. So that's why I put canonical here, right?
So if it was like trivial bundle, then...
If it's a pullback bundle, then this map is actually, this isomorphism is just pullback. Yeah. It doesn't matter which connection you choose, I think. So...
Well, I mean, I said trivial because then you could pick the trivial connection or something.
Oh. Right. So.
Yeah, but yeah.
Yeah. Right. Yeah. So, so let me just say again. So, how is this map defined? So, what I do is I take this beta instanton, and I'm going to denote by B of A naught. What I do is I think of the horizontal distributions of this connection, and I parallel transport those using this Ehresmann connection. And that gives me a connection on P. Okay. Then I twist that by the pullback of some flat connection, gamma zeta, which is some flat connection on a line bundle over Y with holonomy zeta that's specified by this zeta. Okay, so I need to tell you why this is an isomorphism. And the reason is, I put these words integrability theorem, but what is the actual integrability theorem that you use in this case? So we prove the following sort of general integrability result in this same paper. So the result can be phrased as follows. So now I just have some arbitrary principal G bundle. Okay. And I'm going to let A and A prime be smooth connections on P such that they both satisfy these curvature vanishing conditions. Okay. So then there exists a unique, I'll explain what this fiber-based means, gauge transformation U such that U A and A prime are gauge equivalent via U if and only if their restriction to the bundle over this base point is the same and their horizontal holonomy is the same. So what this fiber-based means it's just the identity at this y0, this gauge. Okay. So let me just quickly say what the picture is here. So the picture is, let me think about the case when, so here's the picture. Let's just for simplicity think about the case when y equals S1. And I have these two connections, A and A prime, that restrict to this base point to be the same. Okay, so what I'd like to do is, so here's my S1, here's my base point, and here's some arbitrary other point on the circle. Okay, so what I'd like to do is, I'd like to solve for a gauge transformation along some arbitrary path, and then I want to show it's independent of the path. Okay, so let me first choose a path gamma and solve for a gauge transformation U gamma along this path. Okay, now what you actually do is you solve for a gauge, so I can write the difference of A and A prime in this way. Okay, so this is just, I'm just writing the sort of the 0, 1 and the 1, 0 part of this one form. Okay, so what you actually do is you solve for a gauge transformation along a path here for which this component vanishes and this component is sort of horizontally constant. Okay, and then you use this condition to see that at this point this component is 0. So since it's constant, it's 0 along here, and then they're gauge equivalent along this path. Okay, so, but let's suppose we've done that. So I've solved for a gauge here. Now I solve for another gauge along some other choice of path gamma prime. Okay, and I want to know, do these gauge transformations have the same value here or not? Okay, so you just compute. So you compute the value of this gauge transformation, U gamma at y1 times the, let's see, how do I want to do this? U gamma prime, sorry, okay. So what is this? Well, the point is, when you solve for this gauge transformation, you're essentially solving this ODE, nabla A prime dy sigma, U is equal to U sigma, to kill this component here. Okay, so you solve this ODE, you see that the difference at these 2 points here is the exponential of this integral along the concatenated path of sigma. Okay, but this is exactly this horizontal holonomy along this path times the horizontal holonomy of the other connection along this path. Okay, so if they're the same, then they take the same value, so it's independent of path. Okay. All right, okay, but you see this I didn't need to take y equals S1 here. I could do this in an arbitrary base. I just parallel transport along an arbitrary path and I show it's independent of path. Okay. Okay, great, so that's the proof. So now I'm going to erase the theorem and explain what the work in progress is. Okay.
But when you mentioned codimension-one case, you mentioned there is a problem with the smoothness of gauge transformation at one point.
Right.
So why doesn't it appear here?
Well, it's not a problem. It's just that, in Yuanqi Wang's case, in Yuanqi Wang's case, what he essentially does is he shows that he doesn't have this H1 factor, and he shows that you can consider the pullback map where you pull
when
back.
When you introduce H1 factor, it already kills that. Right?
So the H1 factor just records this. You can think of it as just recording this ambiguity, right? Yeah, right. Okay, so. Okay, so the natural question to ask is, what about when the alpha charge is positive. So notice that you actually get a lot more out of this result than I've stated. So one thing you get is that if you have a theta, if you have, let's think about the G2 instanton case. So if you have a G2 instanton, then this family bundle, the associated the bundle you get over Y has to be flat. Okay, but this already this puts a lot of topological restrictions on this P. So for instance, in the G2 instanton case, if you take T3 cross X, the fact that the base is three-dimensional tells you the flat bundle has to be trivial. So this P actually has to be a pullback. So it gives you sort of an existence criterion for these alpha null bundles. The other thing it gives you is it tells you that, again, let's think about the G2 instanton case. The bubbling only happens along this Y factor across some finite set of points here, because that's how you know the ASD connections bubble. So in particular, the bubbling loci are all smooth. Okay. And there are no non-removable singularities. I don't know if that was known by any other means in this case, for instance, T3 cross X, when you just have a pullback bundle. Okay, but in general, you expect there to be other sources of non-compactness. You're not seeing them in the alpha at charge equals 0 case, but you sort of expect to see them maybe in the general case. Okay, and one sort of source of this non-compactness can be understood through this adiabatic limit perspective, which is another way that one might have thought of approaching this problem. So in the remaining time, let me try to explain. Maybe I'll take like 5 more minutes. That's okay? Then the ending? Okay. I'll try to explain what this adiabatic perspective is and what you can, what our work is in that direction. Okay. So, right. Okay. So notice that if I have a theta instanton on a bundle P over this product, arbitrary bundle P. So let me call this theta instanton A. So I get a map. Let me call it FA from Y to this moduli space of beta instantons on X just by restricting the connection to each slice. Okay. So it's natural to ask, so if I have some A naught is a so-called, so I will tell you what this word sort of means in a second. Adiabatic limit, theta instanton, one can ask if the map, the associated map FA naught can be deformed for a small epsilon to theta instanton A epsilon on this manifold Y cross X, but where now I rescale the metric, let's say in the following way, where I expand the metric on Y by a factor of epsilon to the -2. Okay. So I'm not claiming that this question makes sense at this level of generality, and in fact, that is kind of part of what we ended up discovering. But the point I want to make is that one thing that you can sort of think about in general is a source of non-compactness being these sort of adiabatic limit connections which arise, the equations for which arise by this formal rescaling process where you rescale the equation by rescaling one of the factors, and in the limit you just take epsilon 0 and you see what equations you get. Okay, so again, maybe at the very end I can say sort of at what level of generality we think this equation, we think this question actually makes sense. But I want to mention a result that I think is maybe not as well known these days, but I think is a very beautiful result, which gives you a lot of information about this type of question. Okay, so the work I'm going to describe here is work of Yingji Hong, and then I'll just talk about this briefly and then conclude with a situation in which I think this makes sense. Okay. So what did Yingji Hong do? So I'm going to take X to be a Riemann surface of genus, closed Riemann surface of genus at least 2, and I'm going to take Px to be a principal now SO3 bundle. Okay. And then I take a bundle over the product for arbitrary closed Riemannian manifold Y, which is just isomorphic over the slices to this reference bundle. Okay. Actually, I need a slightly different condition, which can be phrased in the following way. He also needs the condition that the associated family bundle a priori over Y just has structure group, the gauge group here, but I want the structure group to actually be the base gauge group here. Okay, because the moduli space he looks at, which I'll call script M, this is the space of connections on P, which are flat. Oh, sorry. This is the space of connections on Px, which are flat, modulo the base gauge group. Okay, so this is a smooth, finite dimensional manifold, simply connected. So I want the structure group of this associated family bundle to actually be this base gauge group. Okay. So definition. So a connection A0 on P is an adiabatic limit Yang-Mills connection if there exists a smooth family A epsilon of Yang-Mills connections on P over M epsilon. Okay. So over Y cross X, but now with this rescaled metric G epsilon. This rescaled metric here, such that A epsilon converges to A, let's say smoothly over Y cross X. Okay, so this is the adiabatic limit that he considers. Okay, so he just defines the adiabatic limit Yang-Mills instanton, so not instanton, Yang-Mills connection to be one which is a limit of a smooth family of Yang-Mills connections. Okay, and then he proves two very interesting results about this. The first result is that if A0 is such an adiabatic Yang-Mills connection, then this associated map, which is by the same construction I described there, but now to the moduli space of flat connections, okay? Then, so in other words, I impose the further condition that this A0 restricted to each fiber is flat. I get a map here. Then this map is harmonic. Okay. So the residue of this Yang-Mills condition on this family of connections is that the corresponding map satisfies the PDE, which is the harmonic mapping PDE. Okay. Okay, and the second thing he proves is that if the Jacobi operator of this harmonic map is invertible, then there exists a family A epsilon for epsilon small of Yang-Mills connections on P over Y cross X G epsilon. Okay, so you can, if the Jacobi operator is invertible, you can sort of solve this adiabatic limiting problem to recover a family of connections. Okay. So in the remaining maybe 3 minutes, the non-remaining 3 minutes here, let me just say what is the work in progress. Okay. So you see, Yuanqi Wang's work gives you a framework in which it's reasonable to talk about these adiabatic limit theta instantons. Now, what you can do is you can formally compute the adiabatic limit equations from these theta instanton equations. And you find that one has to make a number of assumptions on the form of theta in order to kind of have a reasonable framework in which to study them. Okay, you can make these assumptions and then you can ask whether, so that's just formally setting things up, then you can ask whether the analysis makes sense to prove this result, okay? And then when you do this, you find that you essentially need this condition 1. You essentially need to be in some situation where you have this induced map to the moduli space of beta instantons as harmonic, and then the right assumption to put is that the Jacobi operator is invertible. Okay, you just rediscover that this is the right thing to do. Okay, but this sort of puts a lot of restrictions on the generality, but fortunately it seems to still work in the examples that we care about. So the example which, so lastly I'll just say in the G2 instanton case, what you can find is that you can take the adiabatic limit, an adiabatic limit G2 instanton, I've lost my ability to spell, A naught is the following data. So I can think of the adiabatic limit equations as giving me the data of a map from Y to the moduli space of ASD connections on X is a map with, there's a linear PDE on this map which I can describe in terms of the connection by a theta wedge FA11 is equal to minus FA11. Maybe I'll write it in this way. Okay. So this is the adiabatic information. This was already known. A lot of people had studied this. Okay, but you might ask sort of what is the PDE here? So what is the analog of harmonic map? So this PDE turns out to be, in the case when Y is T3, this PDE is the so-called Footer equation. Okay. And then using the fact that you have a 3 torus across some hyperkähler manifold, you can prove an energy identity for the Dirichlet energy of this map, at least formally. So this is really not the right way. I mean, this thing might not be smooth. So really, it's better to work with sort of a section of an affine bundle. But at least formally, you can look at the Dirichlet energy of this map using this energy identity, and you see that if A is an adiabatic limit G2 instanton, then the Dirichlet energy of this map is exactly the alpha charge of the bundle. Okay, so this together with the fact that in this case you have a nice energy identity, together with Yuanqi Wang's framework, suggests that it should be possible to sort of do the analysis in this case and recover a family of G2 instantons. And possibly also in the spin 7 case where you take T4 across some hyperkähler manifold. Okay, so that's what we're working on now. All right, thank you.
Any questions? Quick questions? Still in the slate. Do you think this construction, like going back, can you connect that to like a gluing construction, like Thomas Walpuski's thing, the part 2, and to construct more examples of, say, G2 instantons? So kind of it seems you're like one of the goals is to show any non-compactness would appear because of flutter sections.
Yeah, right. I mean, if you just rule out
Because
bubbling.
this was like a conjecture for like a long time. I don't know what version of this is correct though. It might not be correct in general.
So what would be nice to show, so what Yunqi Wang doesn't actually show is the reverse part of this, which is that you might like to ask if you have a family of these Yang-Mills connections.
It must be that.
But of course, you have to put some assumptions to rule out just sort of that they bubble. I mean, they might just bubble, but you might like to know that sort of if you knew that with bubbling ruled out, they did converge to some adiabatic limit, then what he's constructing is like a sort of like a bicollared neighborhood of these adiabatic limit solutions.
It's not probably correct in the case of G2 instantons, right? For instance, it's expected to get like one-dimensional singularities, let's say. How do you think that would fit with this?
Well, I think the point is that that is for an arbitrary sort of compact G2 manifold. But here's only the product case. Yeah. So the interesting thing is to see that only in the product case whether that doesn't happen. Yeah.
And how do you say no bubbling? What assumption?
Well, I think you can say like the C0 norm of the curvature is like uniformly bounded or something like this.
Do you see that in the in the analysis though? Like I mean.
Yeah, you do. You do see that actually, because sort of what happens.
It prevents energy concentration.
You need to prove some kind of a priori estimates, which are some sort of elliptic type estimates in the way that like de Stoglu and Salomon do. Yeah. And when you do this, you find that the constant you get in the estimates, so you have some sort of constant which is uniform in epsilon, but the constant depends on in particular on the C0 norm of the curvature. Yeah. So the estimates would break down if that happened. Yeah.
Okay. Any other questions? If there isn't any other question, let's thank you. Let's run to get yours. Okay. They always don't let you on the plane.
Or you have a plane to catch?
Yeah, I have to.